The baseline for aviation archaeology is usually a wide scatter of fragments. When an aircraft strikes the earth or ocean, kinetic energy systematically dismantles the primary structure, turning aluminum frames into shredded fragments. But the recovery of the Junkers Ju-52/3M trimotor transports, the Ju-52 workhorses, from Lake Hartvikvatnet in Norway, presents a completely different forensic reality. The objective for the recovery teams was not to map a debris field or sweep a grid for shattered components. The goal was to extract remarkably preserved, largely intact airframes from 246 feet of Arctic water, intact enough to become museum centerpieces, even if some major components were missing, damaged, or later restored from donor parts. Achieving this required navigating a strict physical constraint boundary. Engineers and divers had to figure out how to hoist thousands of pounds of waterlogged machinery to the surface without allowing the necessary lifting straps to crush the fragile, corrugated duralumin skin. On April 13, 1940, a flight of 13 heavy transport aircraft launched on a high-stakes mission from Berlin-Tempelhof. Refueling en route at Fornebu airfield near Oslo, and with at least one aircraft acting as a communications platform, the formation pushed north toward Narvik. Their objective was to deliver mountain artillery troops and essential military supplies to forces engaged in the Battle of Narvik. Weather and operational hazards immediately fractured the formation during the long transit. Ultimately, 11 of these transport machines managed to reach the Narvik area and secure a landing. 2 others, broken away by the weather, were forced down on ice at Gullefjord instead. The pilots did not touch down on a conventional dirt or concrete airstrip. They set down directly on the frozen, solid ice covering Lake Hartvikvatnet. This single geographical factor would dictate the exact physical condition of the aircraft for more than 4 decades, until the first lift in 1983 and the larger recovery in 1986. For nearly half a century, these heavy machines sat isolated in the pitch black, resting 246 feet below the surface. In a typical marine salvage operation, 46 years of total submersion guarantees severe structural collapse. The saltwater environments act as highly efficient electrolytes, driving a destructive galvanic corrosion cycle that rapidly consumes aviation-grade aluminum. Tidal currents and heavy wave action introduce constant mechanical stress, tearing at weakened bulkheads, shearing off engine mounts, and scattering unidentifiable components across miles of the ocean floor. Marine wrecks are almost always found in an advanced state of decay. Lake Hartvikvatnet imposed a completely different set of physical parameters. The deep, isolated basin operated as a natural preservation chamber, defined by cold, freshwater stasis. Because the glacial lake lacked salinity, the water was a far poorer conductor than seawater. That didn't erase corrosion, but it did reduce the reach and intensity of galvanic attack, leaving more room for slow, with localized pitting and oxidation wherever oxygen, deposits, or dissimilar metals created the right conditions. Furthermore, the extreme depth kept the surrounding water temperature near freezing year-round. This thermal baseline drastically slowed any localized chemical oxidation. At 246 feet down, near total darkness and near freezing temperatures limited biological activity and slowed the decay of non-metal materials. With no tidal currents and generally low energy circulation in the deep basin, the aircraft were largely shielded from the constant mechanical tearing that surf wrecks endure. The lake did not destroy the evidence. It simply locked the airframes in long-term structural suspension. This deep water stasis protected much of the aircraft's engineering geometry, leaving large stretches of corrugated duralumin skin surprisingly intact. This specific rib texture gave the transports their required structural strength in flight, but it was highly vulnerable to focused crushing forces. Because the cold freshwater environment preserved this delicate skin rather than rotting it away, it forced recovery teams to treat the heavy transports not as rigid scrap, but as fragile historical artifacts. The lack of severe corrosion meant the planes were technically strong enough to lift, but only if the dead weight was distributed perfectly across the load-bearing frames. Enthusiast groups and aviation historians quickly recognized the unprecedented technical opportunity this specific lake presented. The first of these trimotor transports was successfully salvaged in 1983. This initial proof-of-concept operation verified that the Arctic lake bed held historically invaluable artifacts that could survive the massive mechanical stress of a vertical extraction. It showed that decades in cold, still fresh water had left the main wing spars and fuselage ribs with their load-bearing integrity largely intact. In other words, the evidence hadn't been erased, it had been held in place. But this remarkable state of preservation introduces an immediate procedural question. Investigators had to understand how 10 identical transport machines ended up perfectly arranged on a deep lake bed without suffering any of the catastrophic high-speed impact trauma normally associated with an aircraft lost over open water. When an aviation unit operates at the extreme limit of its operational range, survival becomes a strict mathematical calculation. There is no margin for error when the fuel tanks are empty and the landing zone is a frozen, deteriorating surface. The crews who placed 11 Ju-52 transports on Lake Hartvikvatnet faced an immediate operational trade-off. The spring thaw had already begun to weaken the lake surface. Pockets of slush and deep standing water severely damaged the fixed landing gear of multiple aircraft upon touchdown. More critically, the heavy transports had only carried enough aviation fuel for a one-way transit. The machines were functionally stranded on the deteriorating ice. This severe fuel limitation forced a brutal decision. Crews assessed the 11 airframes on the ice and chose the one with the least landing damage. From the other machines, mechanics drained what fuel they could and transferred it into that single transport. It was enough for one Ju-52 to start, fight through slush, and take off. The remaining 10 aircraft were already damaged and were left behind on the frozen lake. This specific method of abandonment fundamentally altered the wreckage baseline. A standard emergency ditching over open water strikes a dense fluid surface at high speed, and the impact typically shears off fixed landing gear, crushes lower fuselage framing, and shatters cockpit enclosures. But these 10 stranded transports never took that kind of hydrodynamic hit. For weeks, they sat parked on the frozen surface, exposed, helpless, and repeatedly attacked from the air. Until, in May 1940, the spring thaw erased the ice sheet's structural integrity. When the surface failed, the aircraft slipped into the water with little forward speed. Some frames could still twist, roll, or buckle as weight shifted and damaged sections gave way. But the cabins and flight decks flooded, pressure equalized, and the machines sank to the lake bed with far less breakup than a crash would produce. This passive vertical descent dictated exactly where the wreckage would be located. Instead of fanning out into a classic debris field, the Ju-52 transports dropped almost straight down from their original parking coordinates on the ice. The heavy machines settled onto the varying topography of the lake floor. While some descended into the deep central basin, other airframes settled on shallow underwater shelves at depths of roughly 15 to 25 feet. The final resting depth for each machine depended entirely on the localized geology directly beneath the melting ice. Regardless of their final depth, the deferred ice sinking meant that the airframes arrived at the bottom with their primary load-bearing structures completely intact. Fuel left the machines behind, and the thaw lowered them gently into the mud. This combination of operational constraints and environmental shifts defined the precise physical condition of the targets. Investigators now understood the exact geometry of the heavy transports waiting in the cold darkness. The immediate operational hurdle was no longer figuring out how the aircraft survived the sinking, but rather how human divers could safely reach that extreme depth and verify the integrity of the fragile aluminum structures. Surface sensors have a hard-resolution ceiling. A side-scan sonar pulse can map the topography of a lake floor and verify the distinct acoustic shadow of a large trimotor transport. But an acoustic return cannot evaluate the sheer strength of an aluminum wing spar. At that depth, sonar cannot confirm if the primary bulkheads can support a multi-ton dynamic load. To transition from a sonar anomaly to a viable extraction target, engineers required direct human intervention. The recovery of the Ju-52 transports demanded precise physical surveying that sensors alone could not provide. The primary wrecks were isolated in a high alpine environment, located approximately 9 miles from Narvik Harbor. After the initial lift, a major recovery operation launched in July and August 1986. Their objective was to successfully lift 4 more intact airframes from the lake floor in a single sustained deployment. However, targeting the main cluster of wreckage meant operating far beyond standard commercial diving limits. The targeted transports rested deep in the central basin at exactly 246 feet. Reaching this specific depth imposed severe physiological and operational constraints on the recovery teams. The operation required specialized deep water divers to execute a highly complex mechanical workflow in near-freezing temperatures. The pristine condition of the aircraft, preserved by the lake's cold, still freshwater, meant the worksite was structurally intact but dangerously fragile. The divers were not simply observing the wreck for a condition report. They had to construct a heavy-lift rigging system capable of hauling a massive waterlogged machine completely back to the surface. This requirement imposed the strict constraint of decompression rigging. At that depth, extreme ambient pressure drives nitrogen into a diver's tissues fast, leaving only a narrow window of bottom time before a slow, regulated ascent becomes mandatory. Stay too long or rise too quickly, and dissolved nitrogen can expand into lethal bubbles in the bloodstream. So every dive had to be choreographed on the surface before anyone entered the water. The engineers mapped out specific target zones on the aircraft geometry. One dive team would drop down exactly to the port wing route, clear the surrounding glacial silt from the structural node, and immediately begin their ascent. The next team would descend to the starboard side to inspect the heavy engine mounts. The divers had to memorize the Ju-52's structural layout so they could move through the wreck in blackout conditions, guided only by tight cones of artificial light. Visibility management was a critical handling risk during these brief working windows. The deep lake floor was covered in a thick layer of fine sedimentary silt. If a diver misjudged their buoyancy or misdirected a fin kick, they would instantly generate an opaque cloud of suspended mud. At that depth, a single silt cloud could wipe out visibility and freeze the rigging work for hours until the particles settled. The divers had to maintain perfect buoyancy control while physically wrestling with heavy canvas lifting slings and thick steel cables. The primary objective for these bottom teams was to establish a secure mechanical connection between the aircraft and the surface extraction system. They had to physically evaluate the main spar attachments and verify that decades of submersion had not introduced invisible weaknesses into the load-bearing alloy. The rigging plan required threading thick lifting bands completely under the fuselage and around the massive wing roots. The engineers knew that pulling a heavy airframe up through a dense water column would generate immense physical drag on those specific connection points. The deep water divers mapped the lift nodes and prepared the site within their decompression windows. They verified that the primary structural nodes of the 4 selected aircraft remained viable for a heavy extraction attempt, and the physical path back to the surface was clear. But validating the strength of the main wing spars only solved half of the mechanical equation. The recovery teams now faced the precise material hazard of the aircraft itself. They had to finalize exactly how to tension those massive lifting straps against the transport without point-loading the corrugated skin or collapsing unsupported sections of the airframe. An aircraft fuselage is an engineered pressure vessel designed to withstand aerodynamic loads, not the localized crush of a lifting strap. The Junkers Ju-52 trimotor was constructed using a highly specific material geometry that dictated exactly how it could be handled. If a salvage team simply looped standard steel cables around the fuselage and applied vertical tension, the recovery operation would instantly shear the airframe in half. The target required a mechanical lifting solution tailored strictly to its structural vulnerability. The defining structural feature of this transport is its corrugated duralumin skin, a lightweight aluminum alloy stamped into ridges for stiffness in flight. Underwater, those ridges trapped water and increased resistance during ascent. But the real danger was lateral pressure, thin panels that could be crushed the moment a rig pinched inward. Because the lake had preserved that exterior instead of eating it away, the team couldn't treat the airframe like scrap. Narrow lines were out of the question. A wire under tension would bite into the ridges and collapse the alloy like an empty tin can. The only workable solution was to spread the lift over as much surface area as possible, using thick, reinforced canvas lifting bands in place of raw steel wire. Placing these wide bands required a precise diver threading technique. With the decompression clock running, the bottom teams had to tunnel under the fuselage in near black water. The mud of the lake bed had sealed perfectly against the flat bottom of the aircraft. Divers carefully cleared silt and opened narrow pathways beneath the main cabin floor and around the strongest mounting points. They then fed the wide canvas straps through these passages, ensuring the material sat flat against the strongest internal bulkheads. The strap placement had to perfectly align with the heavy wing root spars and the primary landing gear attachment points. If a band was positioned even a few inches off the reinforced internal frames, the upward pull of the crane would bypass the skeleton and apply direct load to the unsupported corrugated duralumin. The divers methodically checked every contact point along the aircraft belly. They ensured that as the bands wrapped upward around the fuselage, they maintained a vertical trajectory toward the surface, without pinching inward against the delicate upper cabin walls. The engineering solution to prevent this inward pinch required a spreader system, rigid bars, or a wide bridle arrangement, so the lifting bands would not converge into a single crushing point. The bands were attached outboard to keep the pull lines straighter along the fuselage sides. By reducing the inward angle of the straps, the engineers minimized lateral crushing force, protecting the corrugated exterior from structural collapse. Once the canvas slings were properly seated and secured to the spreader bars, the structural connection was complete. The divers connected the main lift cables to the extraction system on the surface. The bottom teams had successfully navigated the geometry limits of the fragile alloy and the extreme depth. The transport was fully harnessed and ready to be separated from the lake bed it had occupied for nearly half a century. But breaking the suction of the mud and hoisting the massive load through the water column meant confronting heavy lift buoyancy physics. The recovery crew now faced the irreversible threshold of tensioning the surface crane. A submerged object fundamentally changes its physical mass the moment it breaches the surface of the water. Moving a heavy machine through a dense fluid is a matter of managed drag. Pulling that same machine out of the fluid into the open atmosphere introduces a sudden shift in load dynamics that can instantly destroy a fragile target. The surface extraction system for the main recovery relied on a massive floating pontoon crane deployed directly on the lake. Engineers had to overcome the dead weight of the waterlogged trimotor transport, the immense suction of the glacial silt, and the constant friction of the water column. The job was to reel the aircraft upward in one smooth, shock-free pull from its resting place. The winch operator on the surface pontoon slowly applied initial vertical tension. Far below, the wide canvas slings tightened against the corrugated duralumin skin. The system generated a massive upward force that successfully broke the suction of the mud. The aircraft detached from the lake bed and began its long ascent. The vertical extraction was a deliberate, incredibly slow process. The surface crane pulled the transport at a highly controlled, steady rate. If the ascent speed crept up, water resistance on the wide wings and blunt fuselage would turn the aircraft into a massive parachute in reverse. This fluid resistance threatened to tear the heavy radial engines from their mounts or collapse the tail section. For the majority of the ascent, buoyancy worked in favor of the recovery team. While fully submerged, the airframe displaced a large volume of lake water, reducing its apparent weight on the lift cables. But the flooded interior still added real mass, and the effective load could shift as water moved inside the structure during the climb. The most critical procedural boundary of the entire operation occurred precisely at the surface transition. As the upper fuselage of the heavy transport finally broke the air and water interface, the heavy lift buoyancy physics violently reversed. The volume of the aircraft exposed to the open air abruptly lost all its buoyant fluid support. Simultaneously, the thousands of gallons of cold water trapped inside the unsealed cabin, the empty fuel tanks, and the deep engine cowlings instantly transformed from a neutral internal volume into massive, unsupported dead weight. In a matter of seconds, the tension load on the primary lifting cables and the canvas slings spiked dramatically. The physical weight of the trapped water alone rivaled the dry weight of the entire aircraft. If the winch operator simply continued the continuous hoist through the surface, this sudden onset of extreme weight would either snap the canvas lifting bands or instantly shear the main wing spars in half. To survive the surface transition, the surface crew executed a deliberate pause in the lift choreography. They halted the winch the moment the cabin floor barely cleared the waterline. The heavy transport was held suspended in tension, half in and half out of the lake. The team then waited for gravity to clear the hazard. The heavy internal water volume slowly cascaded out of the open fuselage doors, the shattered cockpit windows, and the various structural drainage holes. The crane cables groaned under the extreme load as the fluid escaped. Only after the internal water weight had fully drained could the operator safely resume the final hoist sequence. The engineering team successfully repeated this high-risk extraction protocol, ultimately hauling a total of 5 complete transports out of the lake and onto the staging pontoons. The massive machines were finally disconnected from the deep water environment that had protected them. But hoisting the transports out of the lake meant dragging the metal back into a highly oxygenated environment. The recovery teams now faced the immediate procedural challenge of managing the airframes as they crossed permanently onto dry land. The moment an aircraft is pulled from a submerged environment, engineers must make a critical handling decision. They must choose between immediately applying aggressive chemical stabilization or rapidly dismantling the fragile structure for road transport. For the 5 Ju-52 transports recovered during the major 1986 operation, the immense physical scale of the airframes dictated the immediate workflow. The massive wingspans and heavy trimotor configuration made intact road transport impractical in that terrain. The recovery teams therefore dismantled the aircraft into major sections directly on the floating staging pontoons. Mechanics carefully unbolted the heavy main wing spars, detached the corrugated tail sections, and hoisted the 3 radial engines off their mounts to break the airframes down into transportable modules. In most saltwater recoveries, desalination dominates the first phase of conservation. However, the environmental profile of the Arctic lake reduced the desalination burden. Because the aircraft had spent decades in cold freshwater stasis, there was no deep salt loading to leach out. But the metal still required careful drying, cleaning, and corrosion control the moment it crossed the surface. Technicians drained silt from low points and applied corrosion inhibitors to exposed joints and interfaces to slow new oxidation as the wet airframes acclimated to the highly oxygenated atmosphere. In the end, they needed complete, display-ready aircraft in national aviation museums. But the 1940 ice landings and the stresses of extraction left every recovered airframe wounded in different places, so restoration became a controlled composite. Engineers would combine the strongest surviving sections to build stable, exhibition-quality displays. Conservators systematically evaluated the salvaged components across the 5 recovered transports and merged the best surviving structural elements. If one fuselage had a crushed lower cargo deck from an uneven lake bed, but possessed pristine upper wing surfaces, it was mathematically mapped for integration with a second airframe. In one documented instance, restoration engineers built a single historically accurate static display by combining major assemblies from more than one recovered wreck, including at least one wing component used as a donor, and mating them to the best surviving fuselage structure available. Mating components from different production serials required careful alignment work and internal reinforcement. The goal was never to achieve flight readiness, but strictly to establish long-term structural stability for a massive public exhibition. The total yield of the recovery successfully placed 5 aircraft into long-term curation, dividing the massive transports between specialized hangars in Norway and Germany. But the salvage operations did not clear the entire target zone. Today, accounts commonly describe 3 major Ju-52 wrecks still submerged in Lake Hartvikvatnet, one on a very shallow shelf and others deeper on the lake floor. Those remaining wrecks, part of the aircraft left to the lake in 1940, were not recovered during the 80s operations. In shallow water, these remaining wrecks experienced slightly different conditions than the deep basin targets, including minor temperature fluctuations and increased light penetration. Yet they are treated as controlled wartime heritage sites and unauthorized salvage is prohibited. The lake functions as a monitored historical area, and the shallow wrecks serve as accessible reference sites for specialized dive teams and underwater survey work. By extracting 5 airframes for long-term preservation and leaving the remaining wrecks where the lake claimed them, the overall effort preserved key engineering history of the airlift while maintaining the original forensic baseline of the Arctic lake bed.